Good afternoon, everyone. We continue discussion about oblique shock waves. Today probably would be the last lecture about theory of shock waves, and next time we will already talk about next subject like nozzles and expansion waves. I would like to remind you that last time we finished at one example that is explaining how to calculate intersection of different shock waves, different oblique shock waves that are directed on different angles. We defined that due to non-symmetric upper and lower part of geometry, which you can see on figure 921, we have non-symmetrically generated shock waves. So there is a slip line that shows direction of flow after shock wave intersection, which is not horizontal. Of course, if theta 1 and theta 2 would be equal, that flow would be symmetric or similar to symmetric, at least slip line would be horizontal. In a case when it's not equal geometry, we have such a case that requires a kind of model or analytical solution. As I already told you, such model is not explained directly in Anderson book because it requires an iterative process, cannot be solved analytically in a pure analytical way. To build such a model, I will use a definition of alpha. I denote here alpha 4 is inclination of slip line in region 4, and according to theory, this inclination is same for region 4 prime below slip line, and according to theory, also pressure P4 is equal to pressure P4 prime due to parallelity of vector of velocity after shock waves. Since velocities are parallel, there is no gradient of pressure in a direction normal to slip line, and there is this consequence of equal pressure in these two regions. Okay. Please let me know if you have questions on this task and on previous tasks that we already discussed before, and I will see in comments and I will try to answer. Meanwhile, I will start to elaborate the model, or at least to explain you how this model is elaborated. We know that angle alpha or alpha 4, we can call it alpha just for simplicity because it's same for region 4 and region 4 prime. This angle alpha is caused by non-symmetric geometry, as I told you at the beginning. So we can assume initial value of alpha as we need because of iterative calculation. We need some starting value, and I propose here to use starting value of alpha for first iteration as theta 1 minus theta 2. Difference between angle of inclination of the body, and it's same as the difference between directions of the flow in region 2 and 3. I would like to remind you that in region 2 we have flow direction same as a theta 1 direction, and in region 3 we have same direction as theta 2 direction. So this initial alpha we need for iterative process. It will be possible to put, for example, Newton method to solve equation system iteratively. Let's build the model. I will show you the model of the flow starting from region 1 and then up to region 4 and 4 prime on the upper side and on the lower side. We can start from the upper side. I will split this screen in two parts. Probably on upper part, I will write transition from region 1 to region 3 and then region 4. Okay, since we already know equations, I will not write you all the equations from the book because they are known. I will just give you references on the book and I will show you these equations as we had them in our previous discussion. So first transition from region 1 to region 3. We calculate in a way that is perfectly known. We will use first theta beta m relation. In such case, I will involve theta 1, probably theta 2, no, theta 2, since I'm writing for the upper part, and beta 2 and m1. M1 is same as infinite condition. We assume that it's not disturbed flow. In M1 and supersonic. In this equation, let's see the number. We can also see here in our previous theory. Where is this theta beta m relation? This one here. It has a specific number in the book. Just let me find this equation here. Just a moment. It's 923. So equation 923. Inside this equation, we do not have just beta. So from this equation, we obtain beta, okay, beta 2. I don't know if it's good or not to write this subscript 2 because we already have region 2. So probably here I will write beta 3. Okay, beta 3. So this beta 3 is this one here, this angle. Now, when I know beta, I will use transformation from Mach number general to normal component. So I will probably just write, I hope you remember this formula, mn mn1 in such case is m1 sine of beta 3. We receive mn1. Having this mn1, we can receive mn2 according to a function. Let me see again if we have this function in our previous discussion. I mean the number. No, we do not have, but there is this relation right here. And in the literature, just a moment, I'm searching this equation in the literature and its number. Yeah, 914. We receive mn2, and then we receive m2 from equation 918. Y2, it's 3. Guys, if I do mistakes, please correct, because this picture here, it has several volume, so I can mistake between them. M3, and this is equation 918. 918. This is Mn2 divided by sine of beta minus theta. So I have a Mach number in region 3, and by thermodynamic relation, I needed to use a pressure ratio, pressure 3 by pressure 1. It would be, I will write here because we need this equation, 1 plus 2 gamma divided by gamma plus 1, and Mn1 Mn1 before the shock wave in square minus 1. It's equation 916. From here, we will know pressure P3 with respect to P1. Okay, and then we will have transition from region 4, from region 3 to region 4. How we obtain this transition? First of all, we need to know the angle of the body. In our case, angle of the body, theta, we will call it theta 4. Okay, I will continue this line here of vector of from volume 3, and this is theta 4 between flow direction in region 3 and region 4, theta 4. Okay, and this theta 4, it will be also related to our alpha direction. We can see that in this picture, direction of the flow is same as slip line direction, and this, okay, let me zoom a bit. This zone here, and this here is our alpha 4, small angle. Okay. Here we will need to make some transition, and then I will write you after we write same procedure between region 1 and 2. So looking to region 1, we will have similar to theta beta M relation. I will need to repeat this process for the lower side. It will use as input theta 1, and then would be beta 2 and M1. Same equation 923. And then from here, I will find beta 2 because theta 1 and M1 are known. So I will have it here. This is value of beta 2. Okay, because it's inside region 2. I know there is some kind of confusion because we have volume 3 and theta 2. We have volume 2 and theta 1 on the same side. But I hope it's more or less clear. And then having same structure as before, I will write also Mn1 for the lower side. It's M1 sine of beta 2. From here, I find also Mn2 according to equation 914 as we had before. And when I find the normal component of Mach number, I will find also total Mach number M2 according to equation 918. In this equation, I will use my beta and theta difference that I already obtained before. So as you see, until now, it's a linear process. And the last equation here is pressure ratio. Pressure 2 divided by pressure 1. According to same equation, I will not write it again. This is equation 916. Inside this equation, we'll just use instead of, oh no, wait. Now we'll also use Mn1, but Mn1 not previously defined, but Mn1 defined in this volume. So step-by-step calculations, preparation step for the part, upper part of volume 3 and lower part for volume 2. Now we have inside volume 3 known Mach number, flow direction, and let me see, and pressure ratio. And for the lower part, we also have Mach number, flow direction, and pressure ratio. Let's find one more definition here. Is this angle right here, the small one. I hope it's visible. Probably it would be better if I choose another color. This angle here for us is what is theta 2. We can see it's parallel. So theta 2 is angle between this horizontal line and our wall, and here is absolutely parallel. So here we have theta 2 as well. So from this relation of angles, we can write that theta 4 is a sum of theta 2 plus alpha. Okay, let's see same thing for the lower side. I will continue line of the flow on the lower side. I will see my angle of theta 4 prime here, and we will have here this value of alpha. Alpha is here. This is alpha, and if I extend more, I will obtain my theta 1. Theta 1, which is defined here as angle between body and horizontal direction. And for this lower side, I can write that my theta 4 prime is a difference between theta 1, which is known, minus alpha, which we do not know yet. Okay. So this relation for upper angle and relation for lower angle, we needed to implement inside our computational model. How we do it? We do it by the following way. Probably I need one more page here in between, but I don't know how to insert it. Just a moment. I will try to see if I can add some additional page here. Maybe not. I will write in an empty space. Okay, I will continue writing, and then we go back to this schematic. So let's write what happens inside region 4 on the upper region of this flow. This one. Okay. Okay, region 4. Inside region 4, I will use same procedure as I wrote you for region 1, for region 3 and region 2. This is region 3, and this was for region 2. Okay, so we use theta beta M relation. In such case, we use theta 4 beta. Okay, let's call it also 4. And Mach number is coming from region 3. So it's M3. What we know from this relation, same as equation 923, same. From this equation, we know already theta 4 and M3. We know theta 4 because we assume initial value of alpha. We assume that alpha is a difference between theta 1 and theta 2 as for first iteration. And theta 2 we also know. So I will rewrite here this equation theta beta M as theta, which was the value here too. Theta 2 plus alpha beta 4 and M3. So we know this part, we know this part of the equation, we just do not know beta, and we obtain beta 4. Now we see the second part is normal component of Mach number equation. Where is it? Doesn't have here. It's 913. This equation 913. It will be normal component. I will call it MN3 because it's placed here inside the region 3. MN3. We already had MN3, but there are not enough letters. So our MN3 we had here in transition. Okay, now we have it in transition between volume 3 and volume 4. Sorry, I will probably need to remove here because volume 4 is not visible. Okay, I will remake. Okay, so horizontal line is our, so alpha here, this angle here is theta 2, and total is theta 4. More or less clear, I hope. Sorry, it's a lot of marks here, but it's not possible to simplify such model. So when we have equation 913, we obtain Mn1, sorry, Mn3 now, 913, and after using equation 914, we obtain Mn4. Yeah, Mn4. This equation Mn4 is a normal component which exits here inside region 4, and then we make a transition to real Mach number M4 due to equation 918. Then we calculate M4 by equation 918. Inside this equation, we need to know beta, theta, and normal component of Mach number. All these parameters we already calculated. Beta and theta we have here from theta beta M relation, first line, normal component from the second line, this parameter here. So we can calculate M4. And the last operation is to calculate transition on pressure. Pressure 4 divided by pressure 3. Pressure 4 divided by pressure 3. According to this equation 916, I will probably write it again. It's 1 plus 2 gamma divided by gamma plus 1. 1 plus 2 gamma plus 1. It's important because I need then to combine two equations together. And mn, it was mn in squared minus 1. mn4 in square minus 1. Yeah, looks like same. After I receive this equation, I need to make transition from pressure 3 to pressure 1. So I write that pressure 4 by pressure 1 would be pressure 4 by pressure 3, my previously obtained function, multiplied by ratio between pressure 3 and pressure 1. And then I will multiply this function right here. This is the first function. And the second function is this one, which I already had before. The value is just a value. It's not should not enter as a formula. I multiply in such a way. So I obtain the value. Okay, let it be value. Okay, some value. A, for example, just for simplicity, it's a ratio of pressure dimensionless value. And then I do same calculation for region 4 prime. I will not write you all like I did for region 4, just step by step. We use same theta beta m relation. Inside theta beta m relation, I use definition of angle of the body theta 4 prime. Theta 4 prime is a difference between theta 1 and alpha. So I will write already theta 1 minus alpha, beta 4 prime, and Mach number in region 2. Here I know this part, I know this part. I will just need to calculate beta 4 prime. Okay. After I know this, I calculate mn, normal component before shock wave. Here it will be my mn2. mn2. Then I make transition to mn4 prime after shock wave. You see, I already do not write you even number of formula because it's absolutely the same as we had for all previous volumes. mn4 prime, formula 914, and then I make transition to m4 prime, formula 918. After make this calculation, we know Mach number. This Mach number will be probably important for future calculations, but it does not go anywhere inside this equation system anymore. It's just like an output, additional output. What we need to know, we need definitely this mn4 prime because it's used also inside the pressure ratio. We will write pressure 4 prime divided by pressure 2, 1 plus 2 gamma divided gamma plus 1, mn4 prime. This is where it goes, this mn4 prime in square -1. Okay. And then let's see. Just a moment, I will check if everything is correct. If it's Mn4 prime. No. Sorry. No, this is why I'm not 4. It's Mn2. And here in this formula, it should be Mn3 below. Now it's correct. I was looking that the value inside brackets should be positive. So Mn2 in square. Mn2 is more than 1, it's supersonic. So if we subtract 1, it remains positive. It means that pressure ratio should be more than 1. Should be more than 1. So this part of fraction of equation should be also positive to have an increased value of pressure. Pressure always increases when flow passes through the shock wave. So Mn inside these brackets cannot be subsonic when flow passes through the shock wave. And then I have same pressure ratio. Okay, I think there is no more space. I will continue on the corner here. I will write that pressure 4 prime divided by pressure 1 would be pressure 4 prime divided by pressure 2 by pressure 1. Okay, this ratio. This formula we already calculated previously. Pressure 2 by pressure 1 is just a value. And this one we calculate in this function here. Okay, also we have a product of two values. Then we obtain this pressure ratio. Okay, let it be value B. So we have value A, which is pressure ratio on the upper side. And we have value B, which is pressure ratio on the lower side. After all these calculations, step-by-step calculation. And then we need to compare. Okay, how we can compare, just let's see. So we have A pressure ratio here and B pressure ratio here. We see if they are equal, more or less equal, or let's say difference between them is not higher than 5%. It means that we chose our alpha correct enough, and we can complete our calculation. So alpha was chosen correctly. If difference between volume 4 and 4 prime does not give us equal pressure A and B, it means we have to move our alpha in one or the other direction. For example, A is smaller than B. So A is smaller. It means that shock wave on part A, I'll mark here as the blue color, is not strong enough. So A smaller than B. We needed to make a shock wave from region 3 to 4 more stronger. Okay, we needed to increase or decrease. We need to decrease alpha, right? So when we decrease alpha, we increase the angle between slip line and angle of shock wave, and this result in bigger value of pressure ratio. Opposite, when B is bigger, it means that shock wave in lower part is stronger. We can decrease by changing also alpha, and then step by step, even by algorithm, by calculation, program can choose which could be this step of change of alpha from one iteration to another. We can find alpha by 3, 4, maximum 5 iterations, that corresponds to equilibrium between A and B. Okay, so A should be approximately equal to B, and this results in some iteration alpha I that you choose according to your algorithm. This is how, this is how calculation of intersected shock wave would be performed. As I told you, this is not so linear process, so we cannot find direct relation between pressure ratio and alpha, mostly because we involve so many equations and theta beta m relation, which is not linear in all this equation system, that alpha cannot be found directly as a function of A and B, or A and B could not be a function of alpha directly, analytically. This is why we choose among different values of alpha, and we find for which alpha it corresponds better. Another way to solve this system could be to choose not to make like how to say smart choice of gradient method, but to make brute force method when you have many values, many discrete values of alpha, and then you plot how pressure changes in zone 4, pressure A changes, and how pressure B changes in zone 4 prime. In a point where these two pressures intersect, you obtain, I want to make a more straight line. You may obtain your solution alpha I that corresponds solution. It automatically satisfies these two conditions: condition on same direction of angle above and below slip line, because we use same value of alpha to calculate volume 4 and volume 4 prime, and it automatically satisfies equilibrium of pressure in region 4 and 4 prime, because we plot, okay, we analyze this ratio of pressure inside our equation by some method of gradient search, or inside the brute force search method. Okay, let's make a short break, 1 minute, and meanwhile you could write your question. Please write your question. I will take a glass of water. Okay, I see we have one question. If it's possible to write alpha without numerical method. I never saw such a method, and I'm not sure it exists, but you always can search in the literature. At least Anderson does not show such analytical method. And since in this model, which you can see, it has mainly four parts: for volume 3, volume 2, volume 4, and volume 4 prime. So equation system is huge. So I am not sure solution of such a huge equation system will result in a more or less compact analytical model. So probably would be much simpler to find numerically. It's not a problem to find numerically because function A and function B, they are quite monotonic. So we will have just one intersection between curve A and curve B. So there is only one solution possible in such a case. Method of Newton or any other iterative method works just perfectly. The main requirement, okay, we can worry is a number of iterations, but can be solved once we choose, let's say, more approximate or correct value of initial first iteration, alpha. As I told you, this alpha of difference between theta 1 and theta 2 gives very good approximation of initial value of alpha, and then convergence happens in 2 or 3 iterations. Usually, I never saw more than 3 iterations required to solve such a system. Okay. This is a positive part. Negative part that probably analytical solution is not so viable or possible, because even if it exists, it will require several pages of formulas and not so simple to operate with such a model. Okay, I see no more questions. I would like to remove some unnecessary text because already explained and recorded. For people who would like to see again how this method works, please watch again this video. And if someone needs in future, I will be happy to help. I think this method is very nice from computational point of view and not so difficult because all equations are in this system are relatively simple, so solution can be obtained in a simple way. Okay, next task, let's say, Anderson shows is also very practical task where two shock waves from the same surface are intersected. In such case, we have different flow structure from previous one. We have not two shock waves. We have just one shock wave and one which is called reflected wave. This reflected wave is required to equilibrate pressure, to make pressure equilibrium. So which are the input parameters to build such an equation system for calculation? Anderson also doesn't show such calculation, as you may see, but this equation here is much simpler than the previous example. Condition to build equation system is same. We have equilibrium of pressure. Okay, so pressure 5 is same as pressure 4, and the direction also same. Okay, direction, because okay, this direction, it means that angle, how we can call it. Here it's not completely correct, this drawing, and I hope you understand why. But please let me know if you found what is not correct in such drawing. Meanwhile, I'm writing here. No, even not. Okay, theta 2. Did anyone find what can be wrong in this drawing shown on figure 22? Let's say not wrong, but goes not so according to our equation system. You can say by voice if someone found. Yes, it's true. Velocity after shock. No, it's theta 2 is different from velocity direction. Yeah, so it's correct. We needed to denote theta 2 like this. Okay, we continue. Let me try. I will work better on this. Okay, more or less now. One more attempt. It makes automatically this line, so I have not so much control on the angle of inclination of this line. But in case if we use directly equations from our favorite book of Anderson, we have to write that theta 2 is this angle, not angle between wall and the horizontal line. Okay. So this should be correction. And if we make such correction, this angle on the top also would be different. Okay, it's not so convenient. I will put here theta 1 plus theta 2. So it's the sum of two angles. So if we denote in a such way that then we can use our equation system we used before and Anderson shows in the book. Okay, so always remember it's one of the most common mistakes in works of calculation of shock waves, that second shock wave has to have a reference from first shock wave, not from initial flow direction or from horizontal. Horizontal is just because flow 1 is horizontal. So this is why theta 1 is defined between horizontal line and wall. In case when we already have second and third and third shock waves, we always must have a reference from previous shock wave, not from first shock wave. So in such case, we have same angle of flow and we have same pressure. Okay, this can be calculated in a very simple way. So let's make the simplest part. I will split this page in two parts. Okay, on the upper part, I will just write. Okay, I made a streamline for you. It's the same as streamline. But on the upper part from this streamline, I will write equations to calculate transition from region 1 to region 5. So theta beta m relation. For theta beta m relation, we use theta 1 plus theta 2. Then beta 5, m5, no, sorry, m1. Okay, this is known geometrically. This is known from initial conditions. So beta 5 is only unknown. We find when we know beta 5, we can calculate all the shock wave structure. Right. Once the angle of shock wave is known, we immediately calculate Mn1, then we calculate Mn5, and then we calculate M5. Okay. That's the process. And after calculation of Mn1, we also can calculate pressure 5 by pressure 1. According to previous formula, let me see, number 916. So this pressure ratio we calculate. We know pressure ratio. Then that's all for region 5. Very straight calculation. Then let's see lower region 1, 2, 3, and 4. So from region 1, I use theta 1, theta beta m relation, theta 1, beta 1, m1. Known parameters, beta unknown, will be calculated numerically. or analytically if you are lucky. Then same as we had for previous calculations. Normal component Mn1, then we calculate normal component after shock wave, Mn2, then we calculate, let's see, M2. After Mn1, we already can obtain pressure 2 by pressure 1. Okay, now probably would be better if I write it in a different place. Just make arrow here. Pressure 2 by pressure 1 according to same 916. Sorry, I have some messages here. I will turn off. This was a transition on shockwave 1, 2. Now I will write transition on shockwave 2, 3. I have theta 2, theta 2, M2. Known parameters are known. I obtain beta 2. After I have beta 2, same. You can see absolutely same operation. So this is why it's so boring to calculate. Or if you already program one set, one iteration, you can repeat this iteration as many times as you want. Just put input values and the program will give you output. So usually it's simple when you have a program function in MATLAB, for example. So you can just call these functions with known input data and you'll receive output parameters in a very short way. Why doesn't the velocity direction change after the reflected wave? Nice question. Nice question. Nice question. I think this is because flow always repeats direction of the body. And since flow remains to be supersonic according to theory of supersonic flows, direction of the body and flow direction are parallel, always parallel. So I think this reflected wave changes only pressure and doesn't change direction. Maybe because this reflected wave is more perpendicular to flow direction, so it just changes pressure. Of course, it acts on value of Mach number. It changes value of Mach number. I think it's because of direction of reflected wave and flow direction, perpendicularity. But I am not sure that it's perpendicular. Maybe it is. We can check in what literature says about this case. Let's see. I think there is no explanation in the book about this question, but I think the answer is same as I told. Reflected wave is perpendicular, considered to be perpendicular to flow. This is why change happened, but only in direction to the flow, not in any other direction. So direction of velocity does not change, only the value. Okay, let's continue with this writing, and I can write mn2 after mn3 and m3. So I know m3 after I got mn2. I also obtain pressure 3 by pressure 2. Okay, and then we will multiply these two parameters, these two ratios, to obtain pressure 3 by pressure 1. But yeah, we can write it. We can already write it. Pressure 3 by pressure 1 is pressure 3 by pressure 2 multiplied pressure 2 by pressure 1. Okay. That's it. So Mach number we know. A reflected wave is, I think it's an entropic wave. It's considered as an entropic wave, is not a shock wave. In such case, stagnation pressure remains constant. And according to isentropic flow equations or appendix A, which represent these equations, we can calculate change of Mach number. Just let me think how is better. Probably I will write you the equations from previous chapter. It would be faster. I will try to find them here. Okay. So we have pressure or pressure ratio. Let's say we need to have pressure. Let's assume we know pressure. It's say 1 unit of Pascal or 1 unit of bar. And then we might find this pressure 3. Just for simplicity, of course, we can continue working with ratios, but usually when we have such a task, we always have initial value, not just Mach number, but also pressure. So pressure 1 is known and the Mach 1 is also known. Okay, and we know pressure 5 from first transition between region 5 and 1 and 5. So we have them different. They are not equal yet, and they should be equal, right? So I can calculate my stagnation pressure in region 3 and use it as a reference, because flow is entropic when it goes from region 3 to region 4. For this, I will use equation 842 from my book, and it says that pressure 0 divided by pressure. In this case, I will use pressure 3 would be a function of Mach number 1 plus gamma minus 1 divided by 2 Mach number 3 in square, and then powered by gamma minus divided by gamma minus 1. So this power is not so nice to calculate analytically by hand. So this is why we have appendix A, which represents thermodynamic properties ratios for different Mach numbers, right? And for different areas, as we may see in the future, as we will see very soon. Okay, here I know all parameters except P0. So I calculate P0 from this formula and use it as a reference. So it's P03, or P03 is same as P04 because it has same entropy as entropic flow. So I use P04 divided by P4, same as P04 divided by P5, because P4 and P5 are same as we defined previously, since slip line exists and flow direction in region 4 and region 5 is same, so there is no pressure difference. So I write in this way. I know already P04 from my previous calculation, just calculated. P5 is calculated between transition 1, 5. So left side of this equation is known, and then I will write that it will be equal to 1 plus gamma minus 1 divided by 2 M4 in square, and then this nice power gamma divided by gamma minus 1. In this equation here we have just one unknown, is M4, and it can be numerically or analytically solved. I think analytically can be solved, of course, and then M4 is obtained. I hope it's clear that this equation is the final in the system. So we receive M4, we receive M5 from our calculation. We know Mach number, we know direction according to direction of the wall. We know pressure in region 5 and region 4. We know practically all. Keep attention that probably would be one aspect that we need to pay attention as well, that between region 5 and region 4 flow may be not as entropic. We can change it. We can check it. When we calculate P05 according to same formula 842, if we get P05 and compare it to P04, we can check if it's same, then flow is isentropic. If it's not same, which is most likely, then flow is not doesn't have isentropic transition from region 4 to region 5. Okay, I think there is no additional explanation about such type of flow. I think it's very interesting because it's more simple than previous case, and we can calculate all like step by step. No need to solve a system of equation like previous case. Just need to solve numerically in some particular cases like theta beta M relation, transition, and also the last equation we need to solve, but not numerically, okay, analytically. That's it for this case. Please let me know if you have some questions about this case. Then I would like to, before we talk about this question, I would like to understand if was clear our previous discussion. Mostly in a part of diffuser calculation or calculation of multiple shock waves. Okay, I do not see any questions asked in the forum. Do not forget that you can ask questions anytime, and I will answer them. Just going back a few steps. Okay, like now we have more information, much more information about shock waves, about interaction of shock waves, how to calculate single shock wave, how to calculate series of shock waves, reflected shock waves. We have a lot of, say, knowledge, much more than before, right, about structure and theory of shock waves and interaction between them. I would like to clarify one more time. I already told this, but if it was not so clear, I would like to repeat just for sure that it's okay, it was understood. The goal of work one is to create flow properties that are favorable. I mean, to reduce possible losses of energy inside 3 shockwave diffuser. 3 shockwaves, 2 oblique shockwave and 1 normal shockwave, as you may see here on this lower part. I already draw you before this schematic, right? All shock waves, they influence on final efficiency. So it's not enough just to adjust first angle of the body to receive maximum efficiency. Since first shock wave influence on parameters on second shock wave and second shock wave influence on parameters on normal shock wave, it should be solved in a system. So we adjust, let's say, independently angle theta 1 and angle theta 2. I think I also will recommend you to see in one of more information in one of the videos I recorded previously. Just a moment, I will find where is this link. It's in our Moodle. Let me check. In this video, I show this process of optimization. I show how I wrote program for optimization of diffuser to account all 3 shock waves in one system, and the changing one of parameters, how they influence on other flow parameters. I'm not sure if it's worth to show one more time, because such video we already have. Just to repeat same thing, it's not so much use. Okay, I open questionnaire on gas dynamics. And just a moment, I will search it. Is questionnaire on gas dynamics 6. I will share with you my screen so you can see the link, and this PDF file with link is on Aprender 3. So I hope this one is visible. I give on each video, I give some suggestions. Probably some other information would be useful, so do not hesitate to watch, to at least to see a list of questions which I explain on other videos. And here on the questionnaire on gas dynamics 6, I show about optimization parameters and their limits, how is made. So it's, I think it's very useful. It's very useful. And also I repeat some theory which I explained to you about diffuser calculation and simulations. Okay, simulations we have. There are a lot of information. Okay, and let me see. We have many other questions. There are many questionnaires about diffuser. Please see them. There are so many times I explained this question. Drag calculation, for example, I ask how to calculate drag on diffuser and then explain. Then implementation of optimization algorithm. So many questions, not just questionnaire 6, but also other questionnaires you may find important to understand all the topic. I hope you will see, and this information will be helpful for you. Okay, I do not have any additional questions for now. Please let me know if you have questions, and I would like to go to next discussion. Probably last for today. Next time I will start Prandtl-Meyer and expansion waves. I think it's nice to start from fresh. Detached shockwave in front of a blunt body. Anderson also shows this relation here. He shows how to calculate some specific points by theta beta diagram. Shows structure, explains different moments. Okay, general is the following, that blunt body shock wave or so-called bow shock wave cannot be calculated purely analytically. I probably already told you that some time ago we tried to calculate geometry of bow shock wave that NASA published a paper with several pages of mathematical model, just equations without any words. Very big equation system to find analytically such a shock wave. It looks very nice, but unfortunately we could not solve it. So I hope if someone can find and could solve it, would be very big advantage or advancement in such calculation, because I never saw such shock wave calculated analytically. But we always can calculate several aspects of this. It's relatively simple to predict delta thickness of or distance between body and shock wave. This delta, minimal thickness, can be calculated also numerically, but the model is not so complicated. If someone of you would like one day to calculate such a structure, I could recommend the literature to read. I think there is no, just let me check to be sure. I think there is no analytical model to calculate like directly, but there is a way solving number of ordinary differential equations to calculate such a distance. Probably, yes. What we can calculate analytically, we can calculate transition on this bow shock wave in point A. In supersonic subsonic transition, we can use theory of normal shock wave, right? And in other points, okay, you can see point D can be used theory of oblique shock wave, right? Because it's already on some theta inclination. This inclined part of shock wave is probably generated by this inclined shape of the body, so we can use theta beta relation and predict the values of inclination, or at least the angle of the shock wave. Size of subsonic region we cannot, or at least I don't know how it's possible to calculate. It's mostly numerical way. Such a task can be very interesting and not so difficult to calculate by numerical simulation of flows. In case of just supersonic flows, it's not complicated because we use constant specific heat, constant gamma and gas constant R. That we use just conventional Euler equations. Implicit model in fluent could give us such a nice profile. Very nice, how to say, exercise if you like to do some study in numerical tool. Okay, what else? So theta beta M diagram for some points of inclined part of bow shock wave and the normal shock wave theory for straight point A. Okay, so stagnation properties after the shock wave can be obtained, but not so much, not the complete flow structure around this body, because it's not simple, cannot be calculated analytically. And okay, some estimations can be calculated. There is a question, won't there be a attenuation area after the shock wave in D? In D? Similar to the case of a column. I could not understand your question. Please, could you explain?
I'm sorry, you mentioned that in point D, the shock wave is mostly caused by the straight slope. So we could probably calculate it based on using the theta angle, and we could calculate the beta angle and maybe some other properties.
Maybe.
But I was thinking maybe it was similar to the case when we had a conic section instead of a wedge, and the velocity change wasn't instantaneous. It had a curve after the.
Yeah. Also keep in mind. Sorry, could you turn off your microphone? Also keep in mind that it's a blunt body, is not a planar body. It's a axisymmetric body, so flow lines are curved. They are not straight lines after shock wave. So anyhow, such a structure can be calculated in the simplest possible way as a solution of ordinary differential equations, not as a simple algebraic model. Even properties on a shock wave cannot be calculated by simple analytical or algebraic model. It should be a solution of differential equations. But yeah, I think it's a very interesting question. If someone would like to study more, it would be a possibility. Please, if you can, for next classes, improve microphone, because it was very difficult to hear your questions. But when you write, it's better. But only the last question I could not understand, sorry. Okay, I think we could finish at this moment, because there is a lot of information yet you needed to see on previous videos I recorded about diffuser. I think when you see questions related to diffuser, you will understand much better what to do and how to do inside work one, and also would be more clear how to simulate shock waves and diffusers. Please start watching these videos. I think they are essential, because things which were already explained in those videos I usually do not repeat. Very few information I repeat again, but some particular things, very special things, they are on those videos, and I recommend all to see, because such things are not written in the book. You can find only with experience, many years work, then would help you a lot in solution of some particular questions on calculation of shock waves, diffusers, nozzles, and other things in compressible flow. So I would like to ask you, start watching these videos. Please do not forget that there is a deadline for work 1. I expect that you solve part 1 soon. Okay, should be maybe 1, maximum 2 weeks solved, but deliver is middle of next month. But do not forget that you need to make format and you need to calculate also nozzle part. So not enough time for just waiting. Please see the book, see the videos. Some questions were explained there, very important about calculation. And then ask your questions next time we meet on Thursday. I think we are going well with our schedule. Hope you can do all in time. Okay. I see there are no more questions, so we could finish for today. And we meet on Thursday, same time as usual. Thank you for participation today.